How we doing, pro pilots? This is Learning Module 3, Chapter 4 of the Turbine Pilot's Flight Manual. We'll be discussing pages 31, page 61 to 68, hydraulic systems. Just an overview of the hydraulic systems on aircraft. Let's talk about that for a minute. Most important thing about the hydraulic system is to understand that fluids are flexible, but they're non-compressible. And that's an important thing. When we talk about the pneumatic system, air is compressible. It has certain characteristics that we have to watch out for, whereas hydraulics, the fluid is non-compressible, and that's an important factor. Secondly, we need to know that hydraulics are liquids flowing through lines, but the key thing is that they, at the end of the hydraulic line, they activate either a cylinder or a jack screw. Now the cylinder pushes a rod out or pushes a rod in, like on the gear doors, the landing gear itself, things of that nature, okay? The jack screw is a rotational device. It's like a small rotational thing that can screw something out, like on flaps. If you see flaps on most large transport category aircraft have jack screws that lower the flaps. So this is a rotational direction that the hydraulic fluid produces. And so we either have a cylinder with a push rod on it or a jack screw that rotates a rod and screws it out or screws it in. But again, that's important to understand that even though it's a fluid, it still has a solid activator or activation thing at the end of the line to make things happen on the aircraft. Second point is hydraulics operate at very high pressures, plus or minus 3,000 psi. We'll find that hydraulics are used in the heavy lifting on aircraft. In other words, on the heavy systems that take a lot of force to operate. The control surfaces, the flaps, the gear, these things, because to use electrical systems would be, you'd have to have such high draw on your electrical things, and the electrical motors to do that would have to be quite large and heavy, whereas hydraulics can do the job very, very easily, very efficiently. Also, we need to know that hydraulics are like levers. They can produce mechanical advantage. Remember on your car, if any of you had a little small hydraulic jack, you can raise with one hand, you can raise a 3,000-pound car by just jacking up and down on the little small hydraulic jack that you find in your trunk. Another point we need to understand is that there's an accumulator in a hydraulic system. Now you don't know too much about that now, but we'll talk about that in due course. The hydraulic accumulator is like a battery in the electrical system. It can absorb shocks to the hydraulic system so that it doesn't break lines and things of that nature, or it can give a backup when some of the fluid is lost in the hydraulic system. It can act like a reservoir to activate say the gear or the flaps. If you'd lost your hydraulic system, main hydraulic system in flight, you could still activate your gear and your flaps on the approach by using the backup accumulator reservoir. Finally, with all power systems in the aircraft, there's a redundancy or backup designed into the hydraulic system. And this is necessary because, like we talked about, many of these controls, particularly the flight controls in the aircraft, are lost when the hydraulic system fails. So they have to have backup on these crucial systems, otherwise the aircraft would get out of control. Now, I guess if you were operating an electronic fly-by-wire aircraft, you wouldn't have to necessarily have a whole bunch of backup. But even on these aircraft, like the Airbuses that use fly-by-wire technology, even their large gear extension and retraction and flap is done by hydraulic systems. So they can say they're fly-by-wire, but they still have hydraulic systems on board their aircraft to do the heavy lifting. Anyway, let's get into the book here. Let's go to page 61 and look at hydraulic power systems. As you can see here, on page 61, hydraulic systems are based on the simple principle that fluids are flexible but non-compressible. Okay, key point number 1, T question. If we go down to the bottom of the pages, you'll note I'm using a different format, larger print, but you can't see the whole page, so we'll see how this works out. It's easier to read, it's easier for you to follow, but it's got its little drawbacks. Anyway, T question at the bottom of that page on the right-hand side. The solution is hydraulic brakes. He talks about a simple piston. He talks about like in your car, a simple hydraulic application. He talks about a simple piston. The brake master cylinder under your foot applies force through a frictionless or flexible brake line to a similar piston in the slave cylinder at the brakes. So a lot of times we talk about a master cylinder, as we see here, and then a slave cylinder where you need the action to take place. So whether it be in a car or the brakes on the large aircraft, the master cylinder is in the cockpit where you put your feet on your toe brakes, and then the slave cylinder is down at the landing gear, usually on the calipers that grip the rotor to stop the aircraft. So let's go to page 62. You'll have to put up with me. This page advance is kind of slow and cumbersome. So on page 62, they talk about the slave cylinder in turn translate the hydraulic pressure back into mechanical force to squeeze the brake caliper. Now we talked about that in the beginning. The hydraulic line goes from the master to the slave, and at the end where the slave is, it actually produces either a rod that pushes, like in this case, or it could be a jack screw which rotates something and can cause a mechanical thing to move. Okay, let's go down to the benefits of hydraulic power in large aircraft. Hydraulic power is especially valuable for heavy-duty applications because it can be drawn directly from the engine power so as to not tax the aircraft electrical system. We talked about this. Gear, flaps, control surfaces. And so these are normal applications of hydraulics. Goes on to say that electrical motors draw tremendous current when they're used for heavy-duty intermittent operations. Now intermittent means, okay, we hit the switch, we need it activated, then it stays dormant for a while, and then we have to activate it to do something else. And so when the electric motors are turned off and on like that, they have to draw current. As we saw in the electrical system, when you draw current, remember how many amps did the aircraft draw on startup? Like 2,000 amps momentarily for just a second. You can't have that going on in the aircraft system on an ongoing basis, so they use the hydraulic systems for this heavy lifting. Okay, let's go down to next T question down here. Okay, talks about find an engine-driven hydraulic system provides another power source for redundancy on critical systems. So again, as we've talked about, you have to have backups on these large transport category aircraft. On your small Cessna 172, you don't have too much backup. But when you're hauling hundreds of passengers, the safety people want you to have redundancy built into it. In fact, FAR 25, that's the FAR under which the transport category aircraft are built, are very adamant about having redundancy built into all the systems in the aircraft. FAR 23, under which your normal smaller aircraft are built, don't have those same rigid requirements. Let's go down to hydraulic systems and their components. Aircraft hydraulic systems operate at very high pressures, usually around 3,000 psi, and sometimes at high temperatures. That's another important point to note. So this fluid has to be really, really flexible. It has to be able to operate at high temperatures and high pressures, and it can't foam or do other things like that where it gets air involved, because anytime we have air we get vaporizing, you get compression, expansion type stuff going on, and that's not, the hydraulic system will fail if that happens. So it goes on to state that these hydraulic fluids are specially formulated to withstand these conditions without vaporizing. He talks about, vapor or air getting into the hydraulic lines can be chaotic as far as their operation. Now it's coming back from a flight in Phoenix, from Phoenix to JFK, and I noticed that when we were landing on the approach, you could hear some things going on down underneath the aircraft, down, in the lower part where the baggage is. And that is your hydraulic pumps being activated for the flaps, extension on approach, gear, those type of things. So don't be surprised when you hear these unfamiliar sounds going on. It's simply the hydraulic pumps being activated to produce the desired result on the approach. Okay. Again, up here they talk about the the vapor lock. You could get that if the hydraulic fluid was not built to this high standard where it can withstand high temperatures and high pressures and not produce vapors that cause problems. Let's go down to hydraulic pumps and their components. The hydraulic pumps are generally rotary pumps. So you got we'll talk about some other types of pumps later on, fuel pumps, things of this nature, and so they're kind of like gears meshing together. And sometimes we have geared pumps, sometimes we have vane pumps. So these are rotary pumps that go around, coming right off the aircraft's engines. Or sometimes in a standby configuration where it's an isolated application, maybe a trim thing on a control surface or something of that nature. They may have an electrically driven pump in a small area that would be used. These, as says here, these pumps convert the rotary motion of the power source to hydraulic pressure and flow, which is then delivered to the mechanical system around the aircraft by hydraulic lines. Again, that mechanical system, it's either a jack screw or a cylinder with a rod pushing it up, linear out in. Okay, let's go to the next page here. Well, gee, we've got a few other questions down at the bottom here. That's the trouble when you don't have the whole page. So we're talking about the hydraulic pumps and components. So he talks about a hydraulic motor, and the hydraulic motors are relatively small units compared with electrical motors that convert hydraulic power back into mechanical power. And as he talks about, these are basically rotary, like the jack screw, or you can have a cylinder with a push rod that either pushes or pulls in a certain direction. Next, when he talks about these hydraulic cylinders or pistons that translate hydraulic pressure into linear mechanical movement. Then he talks about the hydraulic cylinders are also used to power control surfaces, gear doors, those other type of things. Okay. Now on page 63, we've got a simple diagram of, like in your car, you have the master cylinder here, and you have the hydraulic line going to the slave unit. In this case, it would be the hydraulic, not the hydraulic, but the brake shoes that would compress around the rotor and stop the rotation of the wheels or whatever we needed. And as you can see here, let's talk a little bit about the mechanical advantage. You have a small cylinder that goes quite a ways, and then you have a larger area slave cylinder that has a larger area, and this may have to move 10 inches at 10 pounds, where this will move 1 inch at 100 pounds. So this, simply your foot can generate through, won't call it mechanical advantage, we'll call it hydraulic advantage, to produce a large force at this end with a small application. But again, you have to move this quite a bit farther, this cylinder, to produce the same, or to produce some movement on this larger surface here. Just like I talked to you about the car jack. With one hand you can jack up a 3,000 pound car, but you have to put in lots of movement on the jack handle to get it to come up. Okay, he talks a little bit more about it down here, the mechanical advantage, and you have a 1 square inch master cylinder traveling quite a distance, and then it pushes this larger slave cylinder a very small amount, but it exhibits a much higher pressure, like 100 pounds. You do 10 pounds here and you get a 100 pound output force on this end. Let's go to page 64. Okay, again, we're talking about hydraulic pumps and components, and talks about the hydraulic lines. We've talked about those. The great thing about them is you can wind them all over the place and they maintain that same pressure as long as the line is not compromised with a hole or something like that. And that's why the lines have to be very high quality, because they have to be able to handle 3,000 psi on the line itself. It talks about the valves. Valves direct the flow of hydraulic fluid and therefore power to where it's needed. Like with the cylinder that pushes the rod, you can have the valves can direct the fluid to flow in a certain direction, which will extend the push rod, or it can reverse the flow and it can pull the rod back into the cylinder itself, as with the gear doors. And so the valves are important to understand how that operates. Same with the jack screw. You push the fluid through the jack screw a certain direction and it will rotate in one area, one direction. The hydraulic fluid, change the valve and it will reverse the flow and reverse the direction of the jack screw rotation. Now it's important to know that the valves a lot of times are electronically activated. Now, what would we call an electronic device that changes a valve direction? We'd probably call that a servo, wouldn't we? Or you could have a relay that pushes a valve a certain way. Or a solenoid. A solenoid also extends or retracts a rod to change a valve direction. So these are just some of the things. That's why we talked about electronic stuff before we got into hydraulics, because a lot of the hydraulic valves are electronically activated. He talks about, and I'm not going to spend a lot of time on the hydraulic fuse. Let's just see what the T question on here. If a leak develops in the hydraulic lines or subsystems, a hydraulic fuse, I'm over here, prevents excess fluid loss while still permitting operation of remaining hydraulic system components. And he explains it a little bit more detail down here on this part of the T question. If the fluid passing through the fuse becomes excessive or high rate, like there's a break in the line and it's spilling out, as in a rapid flow towards a hydraulic brake, the fuse closes to shut off the flow, thus isolating the area with the damaged line. So that's what the hydraulic fuse does. It's kind of like a check valve that if the flow gets going too fast, it will stop any more flow from going through there. Now here, the next portion is quite important, the hydraulic reservoirs and accumulators. Let's just stop and look at this for a moment. Hydraulic reservoirs are required to retain adequate fluid level or adequate fluid to operate the aircraft system, as well as some reservoir to allow for leakage. Now this is important. Remember our water wheel analogy? We had things going back to the reservoir. Also, it's important to know, like electricity, that hydraulic fluid has to return. It has to go in a circular motion. Otherwise, we'd have to have hydraulic fluid just spilling out overboard when it was used to activate something. We can't really have that, so we have to have return lines, flow lines going out from the pumps to the gizmo that needs to be activated, then the return line coming back to feed the reservoir so it can be a continuous loop. So you have high pressure going out to the gizmo that needs to be activated at 3,000 psi, and then it says usually low pressure air. Okay, we see it coming back. Here he talks about low pressure air being applied to the reservoir to maintain, minimize foaming. We talked about that earlier. Now, what is an accumulator? It's an important thing. We talked about in the opening session. We said an accumulator is like a battery in the electrical system. It can absorb shocks to the hydraulic system. For some reason there's a spike, and instead of 3,000 psi there's like 3,500 or 4,000 psi put on the system. Well, the accumulator, as we'll see, can absorb that shock, and it won't allow the lines to break. It'll allow the shock to be absorbed in the accumulator and not into the rest of the system. More importantly, the accumulator forms a backup. If there is a leak in the system, the accumulator can hold a certain amount of reserve hydraulic power to be used, at, say, on the approach to get the gear down, to get the flaps down. Now it's a one-shot deal. When the accumulator has expired or all the pressure's gone out of the accumulator, you're done. So that's why you don't want to use it until you have to use it, say at the end of the flight when you need the gear down and the flaps for the approach. Now I'm going to come back to this diagram. It's really quite useful to explain how, well, let's just stop here before I go on and give you some detailed information on the accumulator. As we can see, here's the accumulator in the system, but let's go down here. Let's start here at the hydraulic pump. Here you have the pump, hydraulic pump being driven by the engine, and we have check valves in the system going forward, coming through here, and we have, if there's too much pressure, for some reason the pump kind of screws up a little bit and puts too much pressure through there. Some of this can be absorbed by the accumulator, as we'll see, but also there's a pressure relief valve that will push the pressure, open here, and allow the excess pressure to feed back into the reservoir back here, okay? Now, if you need to get it to the gizmo, which is the ideal, that's what we're after, right? So the line goes through here, and the valve, the actuating valve, could put the flow into the gizmo in the direction that it wants. Say it's to raise the gear. Actuates it to have the hydraulic cylinder draw the rod in to pull the gear up into the wheel well. Now, what we'll see here is, remember there's 3,000 psi on here. We'll go down to, let's talk about how the accumulator is constructed, and that will give you a good idea. Okay, page 65, and they've got a nice diagram of how the accumulator works. Not works, but how it's kind of constructed. As we see here, here is the accumulator, and here's the flow of hydraulic fluid coming in from this direction right over here. It can go through here and on to the other parts of the system, but as it goes through here, it pressurizes the accumulator. Now, it's like a dome or a empty cylinder on top here, and inside there we have air or nitrogen, a compressible gas. You know what I mean? It's not a fluid, it's a compressible gas inside there. And this is the important thing here. This is the diaphragm. It's like it could be made out of heavy-duty composite or something like that. Something that will not allow the fluid, this is fluid in here, will not allow the fluid to go up in there. But by pushing pressure on the diaphragm, this diaphragm can move up and down in here depending on how much pressure is put on. Now sometimes they have a diaphragm in here that will move up and down, or they have a piston in here with a certain amount of friction on it, so that as the pressure increases it will compress the spring on the piston. But let's just call it a diaphragm here for as he explains it here. Okay, so as a system, let's go over here to this portion. As the system is pressurized up to 3,000 psi, it comes in here and it pushes on the diaphragm or the piston and compresses it. So it's got this built-up pressure inside there. Again, you got 3,000 psi on this side of the diaphragm, and you got 3,000 psi on the opposite side of the diaphragm or piston. Now what happens once this gets filled? A lot of times there's an accumulator valve that will hold that pressure and that fluid inside there until it's needed. Now some of the older systems just had a accumulator that was in the system itself, so that if the hydraulic pressure was reduced, the pressure that was built up in here would push the diaphragm down and push the excess fluid back into the system and allow you to continue using the hydraulic system. Now you had to be careful with that open system, because if you had a leak, you could leak out the fluid in the accumulator. So this is probably a better system where you actually have a valve inside there, and it will hold the built-up pressure and liquid or hydraulic fluid in there until you need it. And so it won't be lost because there's no accumulator valve down here. So as we see down here, he's got the accumulator valve closed, one-way check valves here, and then if for some reason you lost lost hydraulic pressure, you would use it as you're doing the approach and landing to get the gear and the flaps down by using the accumulator valve opening here, and it would push the excess fluid under pressure down to the gear and the flaps as required. Okay, let's go back up. I'm sure you'll have some questions on that one. So the hydraulic accumulator stores hydraulic pressure in order to provide backup for key operations in the event of a pump failure. Okay. Now, did we have anything on 64 that we needed to discuss before we went up here? Let me just have a look at my notes here. Well, let's go back up to 64 for just a minute. I want to tell you a story. I was flying for FedEx in 1989 out of Syracuse, New York. I flew from Ottawa, Canada down to Syracuse, New York. And one night I came in, landed, went into the pilot's lounge, and there was a lot of activity around there at that point in time, because the UPS aircraft that also came to Syracuse every night out of Louisville, UPS had just bought a big fleet of 757s. I love that airplane. It's overpowered. They call it the cute chick with large breasts. Large breasts meaning big engines. It has a very good power to weight ratio. and it's just a great airplane to fly. Well, anyway, UPS had bought a number of these, and they were brand new, and it flew from Louisville to Syracuse every night, and so we knew the pilots. We'd sit around in the pilot's lounge and BS with them. And so we'd heard through air traffic control that our buddy who was flying the aircraft, the 7.6, that night had a serious problem. It had a multiple hydraulic failure system on this aircraft. Now, the ironic thing was that the 757 was sold to the airline industry on the basis that it was the most fail-safe airplane that Boeing had ever designed. This is back in the 80s. It had backups on the backups, in particular on the hydraulic systems. And so when they found out that this aircraft had had a total hydraulic failure on the aircraft, this was just earth-shaking to Boeing. Of course, Boeing was put in contact with UPS, with dispatch, and they talked to them and tried to get all the problems ironed out. Well, we stood out on the pilot observation deck up there at the hangar and watched our buddy land his 7.6. I mean the 757. And he didn't have reverse available to him. He had some braking, but it was really going to be a touch and go type situation. And so he landed on the long runway there. I think it's about 8,000 feet long. He landed and got it stopped and was able to shut it down, and they towed it in. But this had had a massive hydraulic failure on the aircraft. He had to rely on the RAT, R-A-T. Now, from the electrical section, we know that the RAT is called the ram air turbine. And we'll see that also aircraft have ram air turbines for the hydraulic system. And apparently he had had to deploy the RAT to use on this aircraft, plus he had to use the accumulator backups to get the aircraft down safely that night. Like I said, Boeing was just flabbergasted that they would have this massive hydraulic failure, because this system, this aircraft was designed hydraulically. It was a hydraulic aircraft. Everything was actuated hydraulically and stuff to that nature. So it became a real interesting test case for Boeing's design and that type of thing. Okay, let's go up to page 65. As you can see, this system's not the smoothest with the page advance, but I guess we can live with it. It's a little easier reading for you guys. I thought I'd do that rather than have you squint like we did before. Now he talks about smaller turbine-powered aircraft usually come equipped with hydraulic hand pumps. So this is your backup. You have a reservoir, and you have a hand pump that can use the fluid in the reservoir to activate the systems that you need on board. On the King Air, that's what we had, was a hand pump right beside the captain's right hand there that we could pump down. And like I told you, with the hydraulic jack on your car, we had to pump that. I think it was like 60 pumps to get the gear down. So you really had to work on that thing. You'd work up a sweat getting the gear down, and also you had to plan well in advance. You couldn't pump this thing down 60 pumps in a matter of a few minutes. It took a little while to get that thing down. So if you had to do a missed approach and come back around again and get the gear down, that was a normal thing on an emergency situation. Over here, I don't know why this isn't lighting up, but anyway, in large turbine aircraft having engine-driven pumps as their primary source of hydraulic pressure, electrically driven hydraulic standby pumps are used to supplement the primary pumps to serve as emergency backup. And he goes on to say that generally electrically driven hydraulic pumps can produce the same pressures as the engine-driven pumps, But, and here's the drawback, they can produce that same pressure, but it takes them quite a bit longer to produce that thing. Goes on to say that therefore, when operating high-load devices such as landing gear or flaps using standby pumps, it takes much longer to operate these systems than with the normal engine-driven pumps. Again, you're dealing with a lower energy pump, and it takes a lot longer to drive that system. So it'll take, just like with the hand pump, it'll take you a long time to get the same thing as when it's driven with the engine-driven pumps, if that makes sense. Now here's an interesting concept. Hydraulic power transfer units found on more complex hydraulic systems are hydraulically driven pumps that utilize pressure from one hydraulic system to pressurize the other system. Okay, so let's go back up to this diagram. I wish they would have had this before they got through the diagram, but this isn't the diagram I was looking for. It's on the next page. But anyway, let's just talk about this one while we're here. Again, you've got your reservoir. This would be your left engine-driven pump, your right engine-driven pump, and you've got them powering the system through here. You got your ailerons, elevators, different things of this nature. Okay. Then you've got your accumulator down here, and they've got another accumulator over here with an air bottle on it, doing the same thing basically as this one did over here, but it's a different concept of an air bottle accumulator. Again, it's got air pressure in here which will force the liquid out of the accumulator, I guess tank, if you want to call it that. Whereas this one has the diaphragm in there, and it's built up the pressure. As this pressurizes, it compresses the gas in here, and you can use that as needed for various things in the hydraulic system. Again, pressure relief valve. If the pressure gets too high coming off these engine-driven pumps, it'll just push it back around into the reservoir back up here. But let's advance to page, it must be page 68, where it has the hydraulic transfer units. While we're on it, let's... Okay, here they are. Okay, so we have system A, system B, hydraulic system A, system B, and left engine, right engine. And down here, here's where the hydraulic transfer unit. This is a little rotating, like a jack screw rotational hydraulic motor down here. And by turning on this pump, you can actually, say this system failed over here. Somehow there wasn't any power being driven off the engine. What you could do is you could have this using the right system here. You'd actuate this valve to allow the hydraulic fluid to go through here at 3000 psi. It would turn this jack screw, let's call it jack screw or a hydraulic pump, to rotate this thing, and it would transfer over there. This then would become the hydraulic pressure pump for this system. Does everybody get that? So if this thing failed up here, this thing would then become the backup pump for this, for all the things downstream from there. And again, things would circulate back up to the reservoir and down through here. This would become the power source, and it would be powered off of the right engine. Again, like electrical systems, it would draw some of the pressure. It would put a lot more pressure on this right engine pump. So I guess you'd have to watch that you didn't overtax the right engine-driven pump because of the requirements on the hydraulic power transfer unit. Again, we talk about the ram air turbine. It shows it here that if you turn that on, it would drop it. Usually the ram air turbine is on the belly of the aircraft. It would drop that into the slipstream and it would power the hydraulic system for that. Or the rat, you could have an electric rat that would drop down and generate power for the aircraft also. Now here's your manual gear extension pump. You would have it up here. Again, you'd have to really pump that hard to get the gear down. I don't think they've got that for a large aircraft. This, the King Air had it in there, and maybe some of the executive aircraft have got them, but in a large transport category aircraft, you just wouldn't have a hand pump in there to get the gear done, I'm sure. Okay. So the air turbine hydraulic pump, or air turbine, so you can have a pneumatic, in other words, using bleed air off of one of the engines, you can have an air turbine motor that uses the compressed pneumatic air from the one of the operating engines to power an APU, or an air turbine motor. Or I guess they could also use it off your auxiliary power unit in the back of the aircraft. It would maybe have one of these air turbine motors on it that could power your hydraulic system. Apparently that 757 had all these features on it, and he had to go and use just the basic rat and some of the other backups on the backups to get the aircraft down that night. It was quite spectacular. A ram air turbine, talks about it here, can be used to produce emergency in-flight hydraulic pressure. These work by extending an air turbine into the outside airflow. Spun by ram air pressure, the turbine in turn drives a hydraulic pump, thereby providing emergency hydraulic pressure. Okay, enough said about that. This is tedious going down through these pages, isn't it? And again, he talks, for example, that the Boeing 767 requires a minimum airspeed of 130 knots to maintain, keep the rat going. So I think that wraps it up for the hydraulic system. Again, he's talking about, that's what he says in the last paragraph here. Since hydraulic pressure is kept bottled up between pump and devices it powers, hydraulic return lines generally carry little pressure or flow back to the reservoir. Exceptions occur when the rotary hydraulic motors are powered to operate high-load devices such as landing gear and flaps. Then both the hydraulic flow and the pressure are significant. Remember, like I said, next time you go on a commercial airliner, watch it on approach. On takeoff, sometimes you'll hear a little bit of activation down in the belly of the aircraft when he puts the flaps down for takeoff. But again, the flaps are not extended to a great deal on takeoff, so you probably wouldn't notice that too much. But on landing, you certainly hear the hydraulic pumps going on as they take flaps 15, flaps 30, that type of thing, and then the gear going down, you can hear that the pumps going. So that's one of the things. It's not like the electrical thing where there's always a constant, not a constant flow, but there's a constant load or thing going on. The hydraulic sits passively until it's needed, and then it's activated. And so it's not continuously going off and on all the time like some of the other systems we'll talk about.